So let's get started. I'm going to go over a couple of the MESI policies, and we're going to start with this question since this was requested. So honestly, if you're able to do like one of these problems with like all four like write back policies, then I'd say you're pretty prepared for the exam. I think the professor honestly says the same thing. Usually, like, hey, if you want more questions, just do the same question, but with the other three write back strategies. So we're gonna just try to do this one like all four ways and kind of go with that. First things first, just a little information about the write miss policies. So we have reads and writes, right? So a load is a read, and a store is a write. So we have write miss policies that happen only when we have a write miss, not when we have a read miss. So these are as follows. We have write back, allocate, write back, do not allocate, write through, allocate, and write through, do not allocate. Starting off with write back, right? So in this case, we write to the cache only. We don't write to the main memory. That's what the write back tells us, right? So both write back allocate and write back do not allocate. We go to the cache. We don't go to main memory. I think write back to the cache. So this is really done to save some time because, as we know, it takes a while to go into memory. If you think about it, you have your CPU and you have your main memory. And you got your buses here, right? And usually this takes like, well, in this case it says 20 nanoseconds, like 20 to 30 nanoseconds, which in the world of data transferring can take a long time if you have a lot going on. However, we have caches, and this is located right in like a little spot on your CPU. So if you're taking it right from your CPU, this is only going to take like 2 to 3 nanoseconds. This is a big difference. We always want to take things from the cache as much as possible. So when we do a write back policy, we write only to the cache. So we avoid this 20 to 30 nanoseconds. Now, this doesn't mean that we never go to main memory. We'll go to main memory when we need to. What that refers to is if we have a case where we have to overwrite the value in the cache. For instance, if something was going to take up that specific value, or if we had something like we had to share a value and we needed to make sure that to be shared, you have to get out of the modified state. We'll go into more of that later on. But essentially, in this case, we only write to the cache. Now, the allocate or do not allocate part tells us what do we do in the cache itself. Okay, write back allocate says leave a space in the cache to allocate. And this is saying to actually record your value into your cache. So this is often called an optimistic policy, right? You could think of it smiley face. It's as if you are in class and you're thinking, I hear what the professor's saying. There's a pretty good chance that this is going to be on the exam. Let me take a note on this. Let me allocate a space in my notes for it. That's exactly what's going on here. On the other hand, do not allocate does not allocate a space in my cache. This is called a pessimistic policy, right? This is like saying, if the professor says something in class and you're like, that probably won't be on the exam, I'm not going to put it in my cache. I don't got to worry about it. So even though write back only deals with the cache, we do have to put it somewhere. So what this will actually result in us defaulting to put it into memory. So we're going to actually learn that do not allocate will function the same with write back and write through. But we'll get to that in a moment, and I go over write through. But for write back, just remember write back to the cache. The back or the through tells you where you're writing to, and the allocate or do not allocate tells you, what do I do in my cache? Okay, write through, right? We write through to the main memory. So this is saying I'm going to write to my cache and my main memory, right? Now that tells me what I'm doing, right? Cache and main memory. The allocate bit here tells me, okay, I will allocate a spot in my cache. This do not allocate says don't allocate a spot in your cache. So in the end, our write back and write through for do not allocate is going to really just come down to defaulting to memory only. And we're going to see that both of these guys will play the same way. So in reality, you only need to really learn 3 write miss policies. For write back allocate and write through allocate, and these guys are going to be the same. Okay, so that's just a little bit of each. Do we have questions right now?
Yeah. I wanted to ask for the write back, do not allocate. Oh, never mind. I just saw that you crossed it out. The cache.
Yeah. So even though write back tells us only write back to the cache, because we're not allocating, we're not putting anything in the cache, and we got to save that value somewhere, so it ends up defaulting to main memory. And then write through allocate is saying go to cache and main memory. But the do not allocate says don't put it in the cache. So what are you left with? Main memory. So for different reasons, they both just kind of default to just main memory. So these two are the slightly harder ones, I think, to memorize, especially for write back allocate. Write through allocate is a little bit easier in the sense that, okay, you put it in your cache and you put it in your main memory. But write back allocate gets a little tricky at times because we'll do an example, but you will not have the same value in your cache that you do in your main memory. So because of that, you need a special bit that tells you, hey, what's in your cache is more up to date than in your main memory. This is where we use the modified bit. Nowhere else are we going to be using the modified bit, so this one's always good to keep in mind there. We'll do an example, don't worry. Okay, we got a question in the chat. A, DNA for cache behavior, and W, E, and Y, D for destination behavior. Exactly, yeah. So allocate or do not allocate tells you what you're doing in your cache. Write back, write through tells you your destination. That's a great way of thinking of it. Okay, so anyway, let's get started with this problem right here. So we're going to actually start with the, I guess you could say, easier one of write through, do not allocate. So once again, write through, write back, do not allocate acts the same exact way. So we're only going to do this 3 ways since essentially both of the do not allocates are going to be the exact same thing. But I'm going to do this problem with the other 2 methods as well after we finish this. I think it should work. We should be fine. Okay. So we have direct mapped cache size of 2, right? And we know that direct mapping is going to say that my cache size is going to be 2. So we're going to take each memory address, right? Usually these are represented like this or like this, either parentheses or brackets. And we divide that memory address by the size. So if we have a mem address of 4 and mod it, sorry, and we mod it by the size, right? Because we want to get the remainder. Okay, and this size is of 2. That means this mem address 4 is going to go in the cache block 0. If we had 5, mem address 5, mod by 2, this is going to go in the cache block 1. Just basic modular arithmetic, right? So we also know that we have the write through do not allocate policy. And this happens on a write miss, meaning we must keep in mind whenever we have a write miss. So this is only going to happen when we miss on a store word. So something like over here, over here, over here, over here, and over here. So we got our work cut out for us. Okay, and if not provided, assume each data memory location has an initial value of 4, and each general purpose register has an initial value of 2. So this is also important to keep in mind, because in this example, we're going to need to keep track of the data as well as the cache, because the data is going to kind of tell us where things are going. So that's always good to keep in mind. So I'm going to make a little note to myself over here to say, okay, memory addresses have a default value of 4, and registers have a default value of 2. And our registers are represented by the $ and a T, so let me actually do that for the register instead of an R as well. Okay, so that means anything that's not going to be initialized just gets initialized with one of these values. And this is important to keep in mind, because if it says that you're going to a destination or a mem address and you want to know what's in that mem address, well, it's given to us right here. So anyway, first things first, we have instruction 1, right? This is a load word, and we're loading mem address 2 into T2. So let me draw out my little cache over here. So I'm going to have 0 and 1 for my cache. So I'm going to put cache. And then what else am I keeping track of? We're also going to do this memory access time as well. So let me also keep track of if it's a hit or a miss, right? This is going to be very helpful. You probably can't even see that. Just C for cache, okay. And what else do we need to keep track of? If it's a read or a write. And we'll do the time stuff after, because I think it might get a little too involved if we do it right now. If we keep track of the hit and the miss and the read and the write, then we should be honestly pretty fine with that. Actually, you know what? Maybe we should just do it. All right, so we'll also keep track of the time, right? Because this is saying calculate the total memory access time. So I think at this point we're good. So we have our cache, we got if it's a hit or a miss, read or a write, and the time that it's going to take. I think he should definitely give you more room, hopefully, on the actual thing. Okay, so in this case, our first one here is going to be load word. T2 is going to take on address 2. So the first thing that I want to keep track of is I want to keep track of what exactly is happening to these registers, because this is going to be something that kind of helps me a little bit later on as I go throughout my my problem. So what I'm going to do is I'm going to write on the side over here, T2 is going to be, all right, what is inside of this register? I mean, inside of this mem address. Well, every mem address, right, we know it's either going to be brackets or parentheses. In this case, it's parentheses. And it's going to be a default of 4. So that means inside this mem address is a 4. And that's going inside T2. I need to zoom in. So that means I could put in a 4 here. That's going to be the data value. Now for the address itself, what I'm going to do is I'm going to put that in my cache. So this is going to be 2. Well, I know my little formula here is telling me take the mem address, mod it by 2. 2 mod 2 is 0, meaning that in instruction 1, we're going to put this in our cache at position 0. This was not in here already. This is a miss, and it was a read miss because it's a load instruction. Because of that, we know that we're also given the time that it takes for a miss. So what's exactly going on is I have to go into memory and get this address. So this is means I have to go to TM, time for a miss, 20 nanoseconds. Or in the example that he gave is 30. You know what? I'm just going to use the times up here. Whether it's 20 nanoseconds or 30 nanoseconds or 2 nanoseconds or 3 nanoseconds, it really doesn't matter. You just want to use whatever time he gives. So if he gives like 50 nanoseconds and 5 nanoseconds, what matters is the time for a miss is going to be way more than the time of a cache hit. This is a miss, and this is a hit. So we know this is a miss. So it's going to take us 20 nanoseconds. So this is what we'll do for the first instruction. And again, because it's a load, we're not using our write miss policy. It's only for write misses, not for read misses. Okay. So then we'll move on to the next instruction. Let me just see. Did I get a question? 4? I'm sorry, what? 4 what? Okay. So now we have our next instruction over here, which is going to be an add instruction. Now, an add instruction is an R type, arithmetic. As we know from the past exam, past units that you've done, R types don't go into main memory. They're done exclusively on the ALU, arithmetic logic unit. So because of that, this will not go into memory at all. We're not dealing with our cache at all. So you can leave it blank, or you can just keep it the same with the 2. Technically, the 2 would stay here. It's not changing that anywhere, but everything else we're not using, so honestly, I'm just going to keep that blank. But we do need to keep in mind what's happening there. And what's happening is we're adding together T2 and 1, and we're storing that into T1. So I'm going to make a note. T1 is getting reassigned, and it's going to be the value of T2, which is 4, plus 1. So this is going to be 4 plus 1 is 5. 5 is going into T1. So you see how what we did in T2 in the last instruction is going to help us here. And it's also going to help us for the next part too. So let me go through. Now we have a store word. This is where we might have a problem. So here, right, we're storing T1 into the mem address of the value of T2. That's probably a mouthful, but let's go through that. Whenever I get something like this, I want to break it down. First, get the value of T2. That's 4. All that means is the mem address 4. So all this is saying is take T1, the value inside of it, which is a 5, and store it into mem address 4. Now we're going to be dealing with a write miss. I look in my cache. Let me keep the 2 from the last time. This is a write. And, oops, wrong place. And this is going to be a miss. This value is not in my cache right now. So I need to actually write this in. Okay, what does my policy tell me? Write through, do not allocate. So this tells me put it into main memory only. Do not put it into my cache. Okay, cool. Let me do the memory first, right? Because we're keeping track of that. Over here we have T1, and that's being stored into mem address 4. So I'm also going to keep a list of mem addresses here. Mem address 4 in memory is going to take on a 5. Cool. So now my cache is going to stay the same because of that do not allocate. I wrote it into memory, right? This is going to be main memory over here. I'm keeping track of that, but my cache does not reflect that. So therefore, I wrote through to main memory, but I did not allocate. Okay. And yeah, so let me just double check. Yeah, so the cache does not change. The mem address does, right? Actually, I'll keep track of that because sometimes it asks for the data memory reference string. If it ever asks for the data memory reference string, that's just saying what memory addresses I go to. So in here we went to memory address 2, and in here we went to mem address 4. We didn't update the cache. Okay, so that would be the end of instruction 3. And the time for that, well, I had to go into memory to update this. So time of a miss is 20 nanoseconds. Okay. And we have a question for step 3. Why does store word T2, T1 get put in as 2 into the cache? So the cache doesn't change. This is the 2 that came from here. So I'm not actually allocating anything. If this was allocate, right through allocate, then this 2 would have become a 4. So we'll do this a few different ways. Okay. So now for instruction 4, right? This is saying load word, right? Mem address 4 into T4. Okay? So T4 is going to take on what's in mem address 4. All right, well, mem address 4 has the value 5, meaning T4 now takes on 5. Cool. Now I'm dealing with the memory address 4. Right, I'm going to put that over here. And this is a read miss. So I just deal with regular direct mapping here. It's not a write miss. So I can actually allocate into my cache, which I absolutely should allocate into my cache. So what I'm going to do is I'm just going to replace the 2, and the 2 is going to become a 4. This is just regular cache allocation that we've done in the past. So in this case, right, we just get a 4 over here. So the 2 goes away. Now, you probably were wondering, oh, what would have happened if I allocated that 4 originally? Well, if this 2 became a 4, then this would have been a hit, right? The 4 would have stayed the same, and that would have been a hit, and it wouldn't have taken as long. So you can see kind of the pros and the cons. This is more of a pessimistic policy. It said, oh, I'll probably not need that 4 again. If it realized that it needed the 4, then it would have actually helped because we used it in the very next instruction. It's like that time when you're thinking, oh, the professor says it's not going to be on the exam, and then it ends up being on the exam. Yeah. Okay. So in this case, right, we actually are keeping, we're not having that 4 there, so that is indeed a miss. So because of that, it is also another 20 nanoseconds. And yes, if it was a hit, it would have been only the 2 nanoseconds. Okay. So now we go on to 5. Just want to pick up the pace just a little bit. Right, we have add T4 and 3, which is just a constant, right? There's no mem address bars around it. And that's going to be added to T4. So this is just a simple add instruction. So we know we're not dealing with the cache in this case. We're not dealing with main memory. So I'm just going to block that out. And T4 is going to be T4 which is the value 5 plus 3. This is going to become 8. And that one's done. Okay, a question. So we usually allocate it if it misses once. The initial hit we don't because pessimistic. So it all depends on what our right miss policy is. If our right miss policy was not right through do not allocate, if it was actually right through allocate, we would have allocated the 4. So the 4 would have actually been in this position over here instead of the 2. And because of that, the next instruction needed a 4, it would have been a hit. So it would have saved us a little time. Instead of being 20 nanoseconds, it would have been 3 nanoseconds right over here. All right, so now we have ourselves another store. So here's going to be another example of going into our right miss policy. All right, we got store word T4 into the value 5. Okay, so this is going to be mem address 5. Let me create a little box for that. And I'm putting the value of T4, which is 8, into 5. Okay, I write through to the memory. Now at this point, I see that I am going into mem address 5. I have myself my cache has a 4, and this is a right miss, right? So 5 would have been going in this one spot, but because it's a right miss and I say right through, do not allocate, I'm not allocating a spot in my cache for it. I don't put it in the cache there. So all I'm going to do is update it in memory, which I did right there, and leave my cache alone. So that might be a problem later on, maybe there's another 5 that appears, and that might cause some problems. But hey, that's what our cache miss policy is. So that would be that. And now for the time, because it's a miss, once again, it's going to be 30 nanoseconds. All right, that's 6. Now we go on to 7. Load word T2 is 4. So this time T2 is going to be loaded with memory address 4. Well, memory address 4 has a 5 in it. Let me move this down a little bit. Oh, I can't move that down. Okay. Yeah, so instead of a 4, this is now going to be a 5, because I'm saying put what's inside memory address 4, which is the value 5, into T2. All right, so here, the mem address I'm going to is 4, and this is load. Okay, so it's going to be a read. And what's in my cache right now is a 4. Oh my gosh, look at that. There's a 4 in my cache. I could take it right from my cache. This saves so much time. This is finally, we have a cache hit. Yay. The cache did something right for once, right? So because of that, we use the time for the cache now, which is just 2 nanoseconds. Or wait, what are we doing? This should be 20. I'm getting myself confused because he's using completely different numbers every time. But basically just remember whatever the time of the cache is. It really doesn't matter the exact number. He's not asking you to do the math. Honestly, you don't even have to add it up. It's just whatever the number is. So in that case, that would be it for that one, and we did everything we were supposed to. So that's the end of 7. Yeah, that should be 20, not 30. Yeah. All right, so now we are on 8. 8 is yet another add instruction, so we're not using our cache at all. We're going to add T2 and 1 and put that value into T3. Oh, that's a new register. We haven't dealt with that yet. So what is T2? T2 has the value 5 plus 1 is going to be 6 into T3. That's it. Okay, and with that being said, we're on to 9, which is a load word. So what are we doing here? We're loading mem address 2 into T1. Okay, So instruction 9, I'm dealing with mem address 2. This is a read. And I am putting the value of 2 into T1. Well, mem address 2 was not changed at all, so I'm going back to my initial value, and that's going to be 4. So I could just keep that here in case we need. So in this case, we have the value of 4 going into T1. So this 5 gets changed into a 4. Okay, and now let's deal with what's in our cache. So in our cache, we want to put a 2. We have a 4 in the cache right now. This is a load. I don't see it here because it should go into the 0 spot. So because of that, I am going to say that this is a miss. And because it's a load, I can simply overwrite this 4 and make it a 2. So loads, once again, I can overwrite if there's a miss. If it's a store, that's when I need to take into account my write miss policy, which in this says don't allocate, don't overwrite, don't touch the cache. It's a load, so it's a read. No problem there. So once again, this is a miss, so we talk about the miss time, which is the 20 nanoseconds. So this cache is really not being that helpful, is it now? Okay, and now we go on to instruction 10. Have another add instruction. We're going to add T1 and T3 and put that into T2. So T1 has a value of 4, and T3 has a value of 6. So T1 is going to take on, T2, that's the destination register, is going to take on a value of 10. Okay, and we did not need to deal with our cache for that. Okay, and now we are on 11. Okay. Alright, so 11 is now going to be a load. We're loading in mem address 1 to T5. 1 was never changed to anything. So 1 still has that initial value of a 4. I'll write that over here. What are we doing with this? Well, we're putting this into T5. T5 is a new register we haven't dealt with before. So what is that? 4 goes into 5. Alright, and now we have mem address 1 that we're dealing with. This is indeed a read. We had a 2 in there already. And this 1 finally can use our 1 spot, right? We know that 1 mod 2 would give us 1. So with that being said, I can just put this in to my 1 spot here, as it was a miss. My time is still 20 nanoseconds. That load is done. Now for 12, we're going to have add T5 and 2 and put it into T5. T5 is 4 plus 2. This becomes 6. And this is not dealing with the cache, so I don't have to worry about that. Now we got to store. This one's going to cause a problem. This is going to say store T5, which is 6, into mem address 3. Alright, we don't have mem address 3 written here, so I'll write that over here. And again, this is going to be a write miss. We're dealing with mem address 3. I have a 2 and a 1 in my cache right now. And because this is a write miss, what do I gotta do? Write through do not allocate. I deal with my memory, so this value of T5, which is 6, goes into my memory, and I leave my cache alone. So my cache is going to still stay the same in this case. So it's still going to be 2 and 1. And since this was a write miss, it's still going to be 20 nanoseconds. Then we have 14. This is a load word. We're putting 2 into T6. Dealing with 2. This is a... I just realized I put this in the wrong place. Good job. This is a miss. This is a right. 14, on the other hand, is going to be a read. And 2 is already in my cache, as I can see here. This is finally another head. This one's only going to take me 2 nanoseconds. Okay, and just to confirm, we're doing mem address 2 into T6. What is mem address 2? It has a 4. T6 we don't have written here, so T6 is equal to 4. 15 is going to be add T6 and T1 together, so that's 4 from T6 plus T1 is 4, so that's going to change T6 to 8. This is an add instruction, not dealing with my cache. A lot of these are not dealing with the cache, it seems. So now we have our cell 16. This is another store word. Store T6, which is 8, into mem address 3. Okay, so 16 is dealing with mem address 3. My cache has a 2 and a 1 in it. This is a write, and this is going to be a write miss. I'm writing a new value in. So because of that, I have to take my T6, which is 8. I'm writing through to memory. So this 6 will turn into an 8. And I leave my cache alone because, again, it's do not allocate. All right, and then I have, that's it for that instruction. Because it was a miss, it still is going to be that 20 nanoseconds. And then we have 17, load word. We're loading in mem address 9, and we're going to load that into T7. T7 is one we haven't dealt with yet. Okay. And T7 has a default value of, well, because we never did anything with it, it's 2. 2 plus 3 is going to give us a value of 5 to put into T7. Okay, and oh, I just realized I skipped an instruction. I'm so sorry. 17, not 18. Skipping ahead over here. We're supposed to load mem address 9 into T7. Okay, so we have mem address 9, and mem address 9 was never changed, so that's going to be the default value, which is 4. That is going to get our mem address and load it into T7. So T7 is going to take on the value 4, which is in mem address 9. Okay. And now we have our cache of 2, 1. This is a read, and my 9 is not in there, so this is a miss. Because this is a load, we're going to overwrite. So where is it going to go? Mod it by 2, has a remainder of 1. It's going to get overridden where this 1 is. So we're going to have a 9 there now. We have a 2 and a 9. Because it's a miss, it's going to be 20 nanoseconds. And did I do everything in that step? Yeah. Now I do the add. Okay, T7 plus 3. Well, T7 is actually supposed to be 4 now. So that's 4 plus 3. T7 is now going to be 7. We don't deal with it for an add instruction. The last 2. Store word. We're going to store word. Okay, this is another one of those weird syntaxes. What is inside T7? 7. This is just mem address 7. What am I storing in mem address 7? I'm storing the value of T7. So I'm literally storing the value of 7 into memory address 7. So for 19, I'm going to deal with 7 as my mem address. And this is going to give us a write miss. So this is telling me write through, do not allocate. Let me handle the mem part. 7 is going to take on a value of 7. And I leave my cache alone. Because this went into memory, 20 nanoseconds it is. And finally, we have 20 over here. So this is going to load in mem address 3 into T2. What's mem address 3 has the value of 8. 8 is going to go into T2. At this point, it doesn't really matter, but whatever. We're dealing with mem address 3. This is a read. And 3 is not in my cache. So this is a miss. Because it's a read miss, I can overwrite it. So this 9 is going to become a 3 now. And I finish with the cache with a 2 and a 3 in it. Because this is a read miss, once again, 20 nanoseconds. And this is the finished problem. You don't actually have to add up everything here. I think this should be fine. It's implied that you would add that up to find the total number of nanoseconds there. Yeah, that would be pretty much about it for that one. Questions? All right. So with that being said, did you want to go over another problem, or did you want to go over this with the write back? I guess we could do write back allocate or write back do not allocate. Write back allocate? Sure.
We do right.
So I can copy it. Okay. All right. Question: since we do not allocate on a write miss, we allocate on a read miss. Yeah. So you always allocate on a read miss, no matter what the write miss policy is, because it's a write miss policy, not a read miss policy. Read miss policies are literally you just allocate over it. You overwrite it. It's pretty much what you've done on like exam 1 material. If you gave a cache to write and there were a bunch of reads, you would just like overwrite where it goes, whether you're doing direct mapping or the set associative or whatever it is. He's only going to really ask direct mapping questions. He's not going to overcomplicate this. It's difficult enough, you know? You don't need to, like, overstress it or anything. So, yeah, with that being said, let's do this with write back allocate now. Okay. So I do actually, you know what, actually I kind of want to use this on the other page just so I can have the mem operations and everything here, because like I don't really want to do the like the ad and stuff all over again. Like I feel like it's kind of breaking my brain. But yeah. All right, so this one, I could do this a different color. Let's do red. This is going to be, instead of write through, do not allocate. We're not going to do write back, do not allocate. It's the same exact thing. Anything do not allocate, you just don't allocate. You just go straight to memory. So you just leave the cache alone. So we're going to do write back allocate by popular demand. So once again, this is going to be our cache. We have a 0 and a 1. Same thing. This is if it's a hit or a miss, read or a write. Okay, and the time you can kind of intuit on your own. If it's a miss, use the miss time. If it's a hit, use the hit time. So I'm just gonna leave that part out. I think that part's kind of easier. I mean, the hard part is like just knowing, like, okay, does it go in the cache? Does it not go in the cache? So this time when we do a write back allocate, what is that telling us? Well, a write back allocate is saying go to the cache only, not the main memory. And actually, wait, I don't think this one would work because we're not really doing MESI here. We could try it. I'm trying to think like how we're gonna have the modified bit here. Well, let me see if this would work. Let's try it, and if it doesn't work, then we can always uh, try something else. We might have to do a write through, but don't worry, we'll get through a lot of write back allocates. Okay, so we're gonna start out over here, load word t2 with a value with a mem address 2. So we're gonna deal with mem address 2 first, and this is going to be a read miss. We're starting off the bat since it's not in there, and read miss. I just put it in there. Okay, and that would be the end of that one. Okay, so then we have T2 has a 4 in it, right? Yeah. Then we add T1 is T2 plus 1. Okay, T1 is going to be just 4 plus 1, which is 5. I'm not dealing with the memory in the cache here. Now we have a store word, right? Store word T2. Okay, what's T2? 4, mem address 4. Promise that I have more room. Mem address 4 is going to have what's in T1, which is 4. So I'm going to put, essentially, the 4 is the mem address that we're dealing with. Okay, so in this case, okay, let's see if this is going to work now. So we're dealing with a write miss this time, and we have a 2 in the cache. This is saying write back, allocate. Only deal with the cache, not the main memory. Okay, so actually what I did here was wrong. We're not going to put this in the main memory at all. So that means if it's ever taken, we're going to just keep it from there. So I'm going to keep the 4 as the original value, which actually was a 4. Wait, did I do something wrong here? Add T1, T2 is, that would be 4, and then I'm storing T1, which is a 5. Oh, 5 would have been stored there anyway. Okay, well, point of the story is I don't need to worry about that. So I'm not actually worrying about the data values of these guys for this one, because I'm not putting it into main memory. I'm only putting it into my cache. So I'm storing mem address 4. And because this is write back allocate, I'm going to actually put this into the cache. So I'm going to overwrite the value here. So this 2 is going to become a 4. Now it's kind of throwing me off here, which was why he might not give that, honestly, as the write miss policy here is technically you're supposed to have a modified bit in this case. So in this case, honestly, we're just going to kind of think about just an allocation policy as a whole. So this is honestly going to act the same way for write back allocate and write through allocate. So the real only difference is when we really have a MESI case. Because when we have a write back allocate, my cache and my main memory are not going to be the same. So for that reason, I'm going to just honestly do this as a write through allocate just for my own sanity, because we don't have a modified bit, and it's kind of hard to do it because we don't have that modified bit. So with that being said, I'm going to just do this as right through allocate. We'll do a right back allocate on a better problem that actually keeps track of the bit itself. So I allocated a spot here for the 4. And that would be pretty much it for that one. Yeah, so T1 goes there, and so this is going to be really great because what happened in the next instruction? Well, we dealt with mem address 4 again, but we loaded it into T4. So T4 was taking on the address of mem address 4, which is going to be a 5, and 4 is in my cache. This is going to be a hit, a read hit. Okay, so now I don't have to worry about any write misses here. Now we have add. We're going to add what's in T4 and add 3 to it. So that becomes 8. Don't deal with your cache. Store word. T4 gets stored into mem address 5. Again, for my own sanity, we're doing this as right through allocate, since we don't have that MESI bit that is able to kind of help us say, hey, is this up to date in memory or not? So we're taking it right from the memory at this point. The point is here that this is a store, and because it's a store, I'm putting the value of T4, which is 8, in here, and this is going to be a write miss. Anytime you have a write, it's going to end up being a miss. And the reason for that is because even if it's the same value that's in the cache, it's still going to be treated as a new value that's getting overridden. So you're going to have to still go into the main memory and actually get it to whatever value you want. So in 6, we're dealing with mem address 5. We have a value of 4 in there right now. And since this is a miss, what does it tell us to do? Right through allocate. So we're actually going to allocate a spot. So I'm going to put the 5 into the place that it's supposed to go. This 1 here. Since 5 mod 2 is going to give us 1. So we've allocated a spot in the cache for it. Then we have 7. So that's going to load 4. Mem address 4 is what we're dealing with. Into T2. What is mem address 4? That's the value 5. So that's going to give us value 5 into T2. And we have a 4 already in our cache. So this is going to be a read hit. Okay, going on to 8, we have add T2 and 1 and put that into T3. So T3 is going to be 5 plus 1 is 6. And that's not doing anything in our cache. 9 is going to be load address 2 into T1. So we're dealing with T1, address 2. Address 2 does not have a value given, so address 2 has a value of 4 by default. Okay, T1 is going to take on that value, so that's going to be, that is not the right one. T1 is going to have a value of 4. Okay, and in this instruction in our cache, what's going on? Well, we have a 4, we have a 5. This is going to be a read miss. It's not in our cache, so we have to allocate a space for it since it's a read. So this 2 is going to overwrite this 4 over here. So we're going to have 2 and 5 in our cache. All right, 10, we have an add instruction. We're not dealing with the cache. This is going to say T1 plus T3. 4 plus 6 is 10. Store that in T2. Load word for 11. Address 1 into T5. What's address 1? It was not defined. By default, it's 4. T5 is going to take on the value of 4. We are dealing with address 1 here. And we have a 2 and a 5 in our cache. This is going to be a read miss. Overwriting the 5 with a 1 since that's the spot. Then we're going to have add T5 and 2. T5 is 4 plus 2 is 6. That gets stored right there into T5. All right, and that we don't deal with. The cache, then we have 13, T5, store that into address 3. Okay, we have a question in the chat. So in write through allocate, everything is allocated to the cache. Yes, so write through allocate, what is it telling us? The write through tells us cache and main memory. Do not allocate, allocate tells us actually allocate a space in the cache. So it's saying do both. Write through to main memory and your cache, and make sure you have a spot in your cache as well as your main memory. Write back allocate would only be the cache, not main memory. And that leads to a bunch of confusing things. So let's try to get to a question like that, because I think that's going to be a little bit more helpful than this one, honestly. But yeah, the main difference with this one, since we don't have a MESI bit, a modified bit or whatever MESI thing you want. Yeah, we're not doing write back for this one because we don't have the portion, so it's gonna just cause a bunch of problems with like flushing values out to main memory if you have a modified bit because it doesn't show that. And this is really just telling you, hey, how do I handle a do not allocation and an allocation? Because this is going to be different than the blue example with the do not allocation. So you'll see the difference for this. So that's honestly fine. If someone could actually, we're almost done with this, but if someone actually could get one of the problems that has that MESI bit, that would be really good. I'd be happy to do that in all different ways. I think there's like one that deals with all 4 write policies with just one address. I'd like to maybe do that one if someone could get that one. I think it deals with just memory address 1 and it goes through all 4 of them. I don't have access to the problem set anymore since I'm not in the class, but yeah, if someone could just send that. All right, let's finish this up strong. We're on 13, yes. So T5 gets stored into mem address 3. Mem address 3 we haven't defined yet. Okay, what are we storing in there? T5 has a value of 6. Put the 6 in there. And what is going on in our cache? Well, this is going to be a write miss. Okay, it's not in our cache, and we gotta write it in. So where is this going to get written into? Well, we want to put it into 3 mod 2. It's going to be 1. So it's going to replace this 1 over here. Alright, then we have ourselves the next instruction, load address 2 into T6. So T6 we have not defined yet at this point. So 2 has a value of 4, so we're loading 4 in there. We're dealing with mem address 2 here. Oh, look at that. 2 is right in my cache. This is going to be a hit, a read hit. Great. Now 15. This is an add instruction. Automatically, I'm not using my cache. And over here, I have T6 plus T1. T1 has a value of 4. T6 has a value of 4. This becomes 8. Now we're going to put T6, store it into mem address 3. All right, so we're dealing with mem address 3. 3 is going to take on the value of T6, which is 8. And okay, we're dealing with address 3. So what's in my cache? I have a 2 and a 3. Oh, wow, look at that. The 3 is already in there. So, actually, would this be a hit or a miss? This would be a miss. Yeah. So anytime that you have a store, it still counts as a miss in this case, because you have to still go into memory and like change the value. Even if the value is technically the same, you still have to go in there. Our computer cache really is not that sophisticated and can't really say, hey, is this value actually equal or is it like a new value entirely? So we just treat everything as going into the cache and updating the value, even though it's the same. I think there's an example in that one that we actually will do with the for policies that kind of has that example, or maybe a different one. But basically, any store that you're going to have is going to give you a miss because what do you have to do? You have to go into memory and change the value. So, because of that, this is going to be a right miss. Essentially, we go in there and we change the value. Yeah, actually, that would make sense because what are we doing? We're changing it from a 6 to 8. How am I going to do that? Well, I have to go into memory and do that. Even though it's in my cache, that address is in my cache, but not the right value inside the address. It'll make a little bit more sense in the next problem where we actually have MESI. So that is 16. And 17 now is load word address 9, mem address 9 into T7, T7 and address 9. 9 wasn't given to us, so that's just default 4. We're putting 4 into T7. Alright, what is in my cache? We got a 2 and a 3. Well, this is definitely going to be a read miss. Change the 3 to a 9 because 9 mod 2 is 1. So that goes in the 1 spot. Okay, then do you mind if I just you know what, let me just finish it. It's the last 3 of them because it's kind of getting repetitive at this point, but it's fine. T7 plus 3, this becomes a 7. So 4 plus 3, 7. Okay, store T7 into, all right, we went through that. T7, what's inside? 7. This is going to say address 7. I'm storing T7 into address 7. So the value 7 is going into the address 7. A little confusing, but so we're dealing with address 7 here. Got a 2, got a 9. This is going to definitely be a right miss. We have to actually update that. So this is not in my cache. I have to allocate a spot. Boom, put it right in there. And finally, 20. This is going to be address 3. So automatically I know this is a 2. This was a 7. This is going to be a read miss. I'm just going to change this to a 3. And that's pretty much it for that one. Yes, I didn't update the last value of T2, but it's fine. Okay, that's neat. I mean, you're not being great on that. You're just being great on the chart. So, when it comes to this, right, the last thing we didn't do is the time, which honestly, it's pretty straightforward. If it's a miss, you add 20 or 30 or whatever time he's using. If it's a hit, then you add the smaller time, which is 20, I'm sorry, which is 2 or 3 or whatever. So actually, you'll notice this, I think, has more hits. We have 1 hit, 2 hit, 3 hit, maybe not. 1 hit, 2 hit. Oh, yeah. So this has 1 more hit, the allocation. And this is because we were optimistic, right? We thought, oh yeah, maybe we'll probably use this again, and for 1 extra time, we did. So it was a lot more overhead because we had to go into memory a lot more. So it might have taken a little longer in some cases, but maybe it helped us in others. So there's always going to be a kind of a balance in there. All right, so that's that one. Questions before we go on? And I'm just going to take a minute to drink some tea. Question, shouldn't write miss be 2 TM? Yeah, I think so. It's whatever time is given, honestly. So in this case, I think he gave 2 for the time miss, or time cache, I mean. It's just really, yeah, you just take whatever times he gives you. The hard part is just figuring out, is it a miss or a hit? Does it go in my cache? Does it not go in my cache? The time, the total memory access time is the easy part. He kind of gives it to you, just plug it in. No on hits. Oh, on a hit, it's gonna just be the smaller time. So you see how we did 2 here and we did 2 here? This is gonna be 2, 2, 2, and the rest are gonna be 20. So this is more of a right. Honestly, it could be for either at this point. You don't have a messy bit, so it's hard to do right back. But the key here is this is for allocate, this is for do not allocate. We did not allocate every time we had a miss. We allocated every time we had a miss. That's the main difference here. For a question like this, do you think he's going to give us? I don't think so. There's no real way to keep track of that. Um, we'd have to like, yeah. There's really no way of doing that because okay, when we do a write back policy, you're going to see exactly why. Because you got to keep track of what's in your cache and what's in your like what's getting overlapped, I guess. Like what's in your cache and what's in your main memory, and because you're not keeping track of your main memory in this case, I mean, you kind of are, but you're not. Whether he if he gives a question like this, whether it's right back or right through, um, it really doesn't matter. All you really care about is the do not allocate or allocate. So that's pretty much it. So if he gives like a question like this, then just literally worry about do not allocate or allocate. The right back, right through is honestly more if you have the actual messy bit. So if you understand how I allocated and did not allocate in specific examples here, then you should be honestly fine. I wouldn't stress as much about this one. I think the hardest part actually with this one, if you understand everything like the other questions, is how to read the instructions itself. So if that's the case, honestly, just remember load word. It's a mem address that gets loaded into a register. Store word is the opposite. You're storing a mem address, a register value into a mem address. I mean, you could think about it. You're storing it where you're storing it in memory. You're loading it where you're taking out of from memory. From memory to memory. Uh oh, good question. Do we need to mark dirty plus 30 nanoseconds on the exam? So I wouldn't worry about the dirty bit. Sometimes he'll give you a penalty. Um, if he does, I think usually you'll add in the penalty for every, I think cache allocation it is, but just follow with whatever he gives you, honestly. This one, he only gave you a time of a miss and a time of a hit, so only go for those. Um, I can't remember if he gave a penalty or not, but I think the penalty is for any time that you go into memory only. So if he did on any of the practice problems, like just let me know, but otherwise I wouldn't worry about that. Like just know, hey, TM, time of a miss, TC, time of a cache hit. All right. I think we're good. Okay. So let me open up this next problem over here. And I'll go on to another one. See, you know it's bad like when I know exactly which problem this is because I think I've done it about like 5 times in the Learning Commons. It's fine. I actually enjoy tutoring this class. Like I kind of like I feel like I enjoyed 343 and 320 like the most. Probably think I'm crazy, but all right. So this one is a little bit more straightforward, and this one is dealing with MESI. So this is going to be a little bit of a different approach. We're only dealing with one memory address. Last time we dealt with many. This time it's just one. So nice and simple. And we're also dealing with the main memory in this case. And you're going to see exactly what I meant with the confusion of, hey, is the main memory up to date? Is it not up to date? What's the big deal? So let's go through it. We have our four different options here. The one thing I'm going to say, again, do not allocate is the same for both of these guys. I'm only doing it once. There's no reason to do it twice. So just to keep in mind, so I'm going to just do these first three. So 1, 2, and 3. So which one should I do first? Just do not allocate. All right, you know what? I'm going to save this one for the end. I'm going to do this one and this one because this is very similar to what we just did. And then I'm going to do right back allocate. And you'll see why. Why is the second and the fourth the same if they have different write-through policies? Great question. Let's go through it. All right. Write back and write through do not allocate. Okay. Write through do not allocate is saying I'm putting my data into mem and cache, right? That's what the write through is saying. But do not allocate tells me, no, don't allocate it into your cache. So it's like kind of overwriting. Mem plus cache, nah, just don't do the cache. You could think of it as like, if you're thinking of, what was that? Like Boolean algebra, like you might have like A plus B complement. It's kind of like what you're doing here. Like you have M plus C complement. So it's like memory plus no cache. So in that case, right, we're going to just put it in our memory. Write back is similar. Write back is saying, don't put it in my memory, but put it into my cache. But, write back actually, more specifically, memory when needed. So don't put it in my memory if I can put it into my cache. But guess what? That do not allocate says, nope, you're not putting into your cache either. Now I'm forced to put it into my memory. Because again, this is memory when needed. Also, if I just said write back, do not allocate, that's kind of like a double negative. It's saying, don't put it into my memory, but don't put it into my cache. What am I doing with the value? Well, this is saying, this do not allocate is taking precedence, essentially. So if you say do not allocate, don't put it in your cache. You're dealing with main memory only. Did that kind of answer your question? Okay. Okay, awesome. So with that being said, let's go into that. I'm going to deal with write back allocate last, just because I feel like the modified bit can get a little confusing. So I'm going to focus on these guys for the time being. Let's do not allocate since we were talking about it so much. So the first thing to keep in mind is we have the initial value of 10 that's given to us for this mem address 1. So we're only dealing with mem address 1 here. So I'm going to start out, my main memory has a value of 10. And this is important because where are we getting this value from? Main memory. So I'm going to have the first one is P1, load word, T1, address 1. So my register I don't really care about. What I care about though is P1. P1 is saying processor 1. C1 is going to be P1's cache. C2 is going to be P2's cache. C3 is going to be P3, and C4 is going to be P4. You get the point. So this is saying in processor 1, so this guy over here, load word, what's in mem address 1? All right, well, what is in mem address 1? The value 10. So C1 is going to have a value of 10. It takes it out of the main memory and puts it in there. C1 is going to have exclusively that value. And what's the important thing about exclusive is if you have something that's exclusive or shared, that means what's in the cache must equal what's in the main memory. It's impossible to have an exclusive or shared if it's not the same as main memory. And this is exactly where that modified bit is going to come into place, because if this is not true, it must be modified. So in this case, we're not dealing with the modified bit, so you don't have to worry about that, but just to keep in mind. So P1 exclusively owns that 10. It's the only cache that has that. Now we have P2. P2 is going to be, let me just keep this guy as the same, store word 2. Okay. This is going to be a bit of an issue, right? I run into a write miss. I have something I need to write. This is not in my cache. I have an issue. So to do that, what is my write miss policy? Write back, do not allocate. Okay, so what did we just go through before? Write back says, give me my cache only, not my main memory. Main memory only when absolutely necessary. But the do not allocate takes precedence. It says, no, I don't want it in the cache at all. So, okay, I'm forced to use main memory. That's the only thing I can do. So this is saying, just don't put it in my cache. So I'm not putting it into this cache at all. This 2 goes straight to memory. It overwrites the 10, and the 10 becomes a 2. But now there's an issue. The main memory is not the same as the exclusive cache. Anytime that there's a write happening, a write bit gets sent on the, you could think of the data wire. And that tells any other caches that are snooping, right? Snooping meaning if this is like your CPU, P1, P2, P3, right? They're all connected to main memory. So if there's a change that happens, right? Processor 2 writes here. A little write bit gets sent. P1 snoops this bit, and it says, oh no, there's a change. My value's not up to date anymore. Because of that, this guy gets changed to invalid. The 10 stays the same, right? There's no need to overwrite it because it's invalid. Why am I going to waste the time to do that? It sees an invalid bit, and that just tells it, okay, I'm not even going to bother going into main memory. Right now, I don't have the up-to-date value anymore. Other than that, this would be kept the same, and that would be it for that one. So that's how do not allocate is working. Next we have P3. We're going to load in the mem address into P3. Okay, well this is just a read miss, so this kind of gets handled just as we would for anything else. All right, I check, is it in my cache? Can I take it from my cache? No. So that's going to be a little inconvenient. I have to go into memory for it. All right, well, mem has the updated value of 2, right? Cache doesn't. Cache has an invalid value, so it says I'm not even going to look at that. And it's going to put it into P3. So P3 is going to take the 2 from memory, and it exclusively has it. It's the only guy that has it at the moment. C1's invalid. C2, we said didn't allocate it, so it didn't write it down. It's your friend who didn't write notes in class, and then they got lost, right? And then main memory has the up-to-date value, so we take it from the main memory. P4, similar. We know that this is what our caches look like right now. This time, we want to load it in. P4 does not have that value. But it doesn't have to go all the way to main memory. It could ask its friend, P3. It's Like, you ask your friend for the notes instead of going to the professor's office hours. It's gonna take more time to go to the professor's office hours than if it does to just message your friend, like, yo, send me the notes, pal. So, to do that, I can just do a simple share. This guy shares over, and now they both have 2 and they both are sharing. They're happy. Sharing is caring, guys. Unfortunately, that's not going to last very long because we have ourselves another store. So this is going to cause a little bit of some problems. We're storing the value 2 into this address. Now, yes, there's already a 2 in here. But again, our processor is kind of stupid. It's not going to check, hey, is this the same value? Because that's going to take up resources, and for whatever reason, they just don't want to do that. So because of that, we have to go through the whole process again. It's going to be a write mess. So with our little example here, this time P2 is once again writing. It's in the right bit. This is going to be a write miss. So what does it say? Write back, do not allocate. Okay, this is saying, well, I have to go into memory because I'm not able to allocate into my cache. So I go into main memory first and I change this guy from a 2 to a 2. Yes, it's the same value. No, your processor doesn't know. Or maybe it does, but it doesn't care. So for that reason, now an invalid bit is sent to all of the previous holders of that value. That means we have, oops, I forgot P4. That means P3 and P4 had this value. They no longer have the same value. I know it looks like they do, but that's not the point. You could just pretend that this was a 3 for all we care. An invalid bit gets sent to them. This becomes invalid. This becomes invalid. Oops, I should probably put that on the next line. Oh, hang on, I'm getting a phone call. Can't really stop the recording. Okay. Anyway, okay. Where was I? We have shared. We got 2, and we got shared. So these guys get an invalid bit that gets sent to them. And C1 we know already had that. Okay, and the last thing is we did not allocate, so this cache still stays empty. So this is what it'll be finished looking at, so if we ever have to get this value again, we gotta go once again to main memory. Alright, so that's the end of the do not allocate one. Any questions on that?
Quick question.
Yes.
I missed like the first half. When do you, if you have an invalid bit, when does it not become invalid? Like under what situation?
Oh, okay. So it has to get a new value loaded onto it. So in the case of this guy over here, let's say, this P2, we have, this one is invalid, right? If we had another thing that said, I'm sorry, this is P1. If we had an instruction here that said, once again, P1, load word 1, that's going to tell us, if like that was down here, that's going to say, okay, get that value. I'd get it from memory because none of these guys have valid bits here. And that would put the 2 here, and it would exclusively hold that. Again, if this first instruction was repeated at the very end over here, so I'm loading in address 1 over here. So that would result in exclusive 2. It overwrites. The I becomes exclusive, and then the 10 would become the 2. So you just have to load in a new value. So you can load in, or
Okay.
if something was stored and overwritten.
Then another question: why can't you share it when another value, like another processor, loads it?
Why can you share it?
Why can you not? So let's say like P3, we get 2 from the main memory. So why doesn't it share that with P1?
Well, Okay, if we're at the very end over here, this is invalid. Even though it's
I'm talking
2,
about line 3.
3. Like over here?
Yeah.
Yeah, it did share it. This shared over here.
No, but why doesn't it share with cache 1 though?
Oh, because it just never asked for it. There was never a line that said loaded into P1. This is saying P2,
Okay, I see.
P3, P4, P2. I only deal with cache 1 here. Cache 1 just never wanted it back again for whatever reason. If there was, again, if this last line was calling P1 again to load that value into P1, then yeah, I would definitely do that. But if it's invalid, there's no request to it. It kind of just gave up. It didn't want the value back. You know, maybe it just finished with it. There's no need to do a load again if you're not actually using the value.
Okay, makes sense.
Cool. Okay. Are we good with this one? Because if so, I can move on to the next one over here, which would be, I could do right through allocate next, the one right below it. All right, so this guy over here is right through allocate. So in this case, remember, right through is saying right through to my memory and cache. So for that reason, we are going to make sure that anytime there is a write miss, we will allocate a spot. So these little blanks over here are not going to happen. And everything in my cache is going to be the same as my main memory. Yes, it's going to kind of waste a little bit of memory on time a little bit, because every single time I get a write miss, I have to go into my main memory and my cache. But, you know, sometimes it's good. There's always a trade-off for everything, so you don't have to worry about that. So now we have ourselves, starting over again, we're given main memory has the value 10, right? This was the start from the very beginning. So we got load in into P1. Okay, so this is just simple. Load was technically a read miss. I take it in from main memory. It takes a little bit of time, but no biggie. That's the end for the first instruction. The second instruction, now I have myself a write. Okay, well, this we know is going to be causing a write miss. So what is my write miss, right? It's not here. This is what my cache looks like before, and it's saying write through allocate. So two things are going to happen. I write through to main memory. Let me handle that first. This 10 becomes a 2. We know anytime a little write bit is sent, I'm going to need to update everything else. So because of that, the original value that had it, right, this exclusive 10 in cache 1, this guy becomes invalid. This 10 still stays, but we treat it as if there's nothing there. It's kind of, they call it lazy deletion. It's like you just delete the reference in a sense to it, so we just treat it as if it's empty, and we can easily overwrite it for any other values. Okay, I did the write through. Great, now I got to do the allocation. Well, anytime that I have to allocate it, I'll just put it in here, and this guy is exclusively the only one that has that value now. The main memory and the cache are the same. So we know that this is valid, and we are all good. All right, now we have ourselves P3, load word, and let me write in the rest of these guys. So this is gonna just load into P3. Now, I can actually take this, is it not C? E to S to I and C1. Oh, shoot, yeah, you're right. Oh my gosh. Thank you for catching that. Let me go back a few steps. Going back to P2. Okay. I missed an important step here. So we changed this guy, right? We wrote him. But this is the thing. Before we actually do the write itself, So actually, before I do this, honestly, I need to handle the allocation part. I don't want to have to go all the way into memory twice. Why would I have to go into memory twice? Well, I need to get the mem address from memory. I need to get the 10 brought here. And then I need to actually do the write. This is going to take 30 nanoseconds. This is going to take 30 nanoseconds. I don't want to have to do that, especially because, guess what? The address is right here. Instead of doing this guy to get the address, I can allocate the address from here, which would only take like 3 nanoseconds. So that's what we're going to do first. We allocate, then we write. I always like to explain it. I have to give you the piece of paper first before you can actually do changes on it. So here, I'm going to share over to C2. These guys are sharing. He has the address. C2 has the address, and C1 has the address. Now I can do my write. I have the paper. I do the write. I write through to memory. This guy gets written. But now he gets backstabbed because this guy was sharing with. This is where that write bit gets sent. And because of that, this is going to be invalidated. This one's no longer valid. Now C2 is exclusively owns this 2. It's the only one that has that value. So whenever we have the write through allocate, handle the allocation first, then the write. Give them the paper to write in the first place. Give them the address. Then you can actually do the writing part. So that's what we're going to do there. All right. So, yeah, that was what I was missing there. So now that we go on to P3. So this guy is invalid 10, exclusive 2, and 2. This is just a simple sharing. I can share this easily with C3. So this guy is going to share over, and now they both have that value. P4 is going to be the same thing, right? I'm just loading in the value. Well, where can I get it from? I could just share it over. I could share it with as many caches as I want. There's no writings, nothing gets changed. There's no problems. It's like you're just sharing your notes with your friends. Now we have an issue with the store. This is going to cause some problems. So with that, what are we doing? All right, again, even though it's the same value, it's still a write miss. We're still going to have ourselves a problem. So what I'm going to do is, I have a write miss. Oh no, what am I going to do? Write through allocate. Handle the allocation first. All right, well, I have the allocation already here, right? The address is here, so I don't have to worry about that. What I do need to worry about, though, is everything else that's attached to it. This shared value is going to change to exclusive 2. This is the new 2. Write a 2. I'm going to just write a 2 star just to show that's like new 2, because it's going to look like it's the same, but I'm going to do the write here into main memory. Oh no, I think my Apple Pencil just died. Oh, now I'm good? Okay. Oh, no, I'm not good. Yikes, what just happened? Okay, so this 2 gets overridden to become the new 2. Because of that write, I have to stay same, this invalid bit gets put down to anything that it was sharing with. So this dude and this dude. This becomes invalid with the old 2. This becomes invalid with the old 2. Okay. Yeah, so actually, yeah, what Pima said in the chat, shared to modified to exclusive, that's technically what's going on. So technically, what happens with write through is I write through to the cache and the main memory. I write through to the cache, and technically it goes from shared to modified. Right? It has a new value to it. I'm just going to use the example of the 10 and the 2 to make it a little easier. It goes from the 10 value from the main memory, then I change it to the 2. It's modified. But because I write through, I change the memory to the updated value so fast that it goes from shared to modified to exclusive all in one stage. So the modified is only going to happen if you have a write, and it's only ever going to stay in that state when you have the write back allocate policy. So that's the only reason why I skipped over that, because he does only really care about the final state. But yes, technically what is happening is you're going from shared to modified to exclusive for each time that you're writing. So this guy over here would technically be going from shared to modified to exclusive. So shared, then you modify the value, it goes from 10 to 2. Then you put it to main memory, and now it's exclusive. And same thing here, shared, modified, exclusive. And that's only for the writes, here and here. The other guys would just go to the invalid. Yeah, and the M to invalid the other, that's what the whole write bit is. It sends this write bit, and because of that, invalid bits get sent to anything it was sharing with. The second something's modified, the second you send that write bit somewhere, then you get those invalids right there. And that's the end of that problem. So if we don't have any other questions, let's do write back allocate. Yeah, don't worry, we're definitely going to do this one. This one's always the most confusing, but we'll be alright. Alright, so once again, starting out at 10. And what do we got here? We got 1 going into P1. So this is just a simple load. Same as always, E10. It's exclusive 10, they're up to date, everything's all right in the world. Next we have P2, store word. This is going to be storing 2 into there. Okay, this is going to be a write miss. It's not in my cache. I got to write back, allocate. All right, handle the allocation first, get the piece of paper, then I can do my write. And how do I do that? Well, I got to share over from C1. So C1, you got to cough it up. Share over to this guy, and now they're up to date. I got the piece of paper, I did the allocation, now I can do the write. I'm going to change the 10 to the 2. Now this guy's modified. Anytime that modified bit happens, anytime that write bit happens, the actual write happens, we change it to invalid. So we go from E to S to I. So same thing here. The only difference is this stays in a modified. I don't flush it to memory because I don't want to spend that extra 30 nanoseconds pushing that to memory. I just saved 60 nanoseconds. Why 60? Because if this wasn't here, I'd have to take 30 nanoseconds to bring the address from memory, the allocation, and then another 30 seconds to send it back to memory. So I just saved a ton of time. So that's the perk of write back allocate. And this would be the end of that line there. So we stay in the modified state. Right, this one we pass through. We pass through so quickly, so we end up in the exclusive state because we did the actual write through to main memory. We don't do the write through here. Next one, we have P3, load word, and we're doing the same address. All right, well, oh no, this is a read miss. It's not there. This guy's invalid. I can't take it from there. And I have a modified and a 2 here. All right, well, the modified tells me, hey, this cache has the most up-to-date value. You gotta take it from this cache. It's like, this is the newest iPhone. You gotta have it. Well, this is a problem though. I can't share it until I get rid of that modified bit. And the only way I can do that is flush it out to main memory. So I gotta flush it out first. So I'm gonna write this 2 to main memory. So that 30 nanoseconds that I saved before, it's coming back to haunt me. Now I gotta pay the price to actually flush that out. Now that it's up to date with main memory, it's exclusive. It's the only guy that has that value. We're all set. Oh, great. Nice. Now it's just a simple sharing. I can just share this guy over. And now they both have 2, and now they're happy again. And the same way it goes with 4, right? This is shared 2, shared 2, shared 2. That 2 is already updated. Invalid 10. Everything's right in the world. All right, now where it's going to get into trouble again is this one over here where we have another write. This is going to write this new 2, which, you know what? I'm going to change this 2 into a 3. Let's just make it a little easier for ourselves. That way it's not so confusing. So, okay, this time we want to take a 3 and we want to store that into our address, into 2. All right, well, right now, C2 has a 2 here. I need it to be a 3 in this case. We got ourselves a right miss. No one else has this address, so I can't share it over from something else, right? So I'm gonna first get that address, right? And then from there, what I'm gonna do is, this is the only guy that has that address, but it's not in, actually no, I'd be taking it from my main memory. Yeah, I take it from my main memory and it's exclusive. Okay, this is the only guy that has that value. And this is fine. I didn't overwrite anything else there or anything, so I should be okay with that. And now in this case, I would take the exclusive value, I modify it, and I don't push this to main memory. This modified bit tells me, hey, guess what? This 3 over here, this is the only up-to-date value in this cache here. So that would be the end of that one. So if it was a 2, if it was the original 2, then at that case, that would mean an invalid bit gets sent here and here. So if that's the case, yeah. So you know what? Let me just bring it back to the way it was before. I'm just going to make this a 2. Just keep it the way that it was. That way you guys could see the invalid bit. So again, it still goes from shared, actually this time it's just shared to modified because we have the 2 already in the memory. Okay, I can't delete that for some reason. Yeah, so that just goes from shared to modified because I already have that in the memory. It's already shared. But now, because this is a new 2, let's just say that's going into play, I could just do 2 star. This becomes invalid, and this becomes invalid. So same as the last one. Can we redo the last line? Yeah, we can just redo that, honestly. Hang on a minute. Why is this not working? Okay. So now we have... The eraser is really weird on this thing. That's why I've been trying to avoid that, but... Oh well. So, anyway, we have... Yikes. Alright, I tried, guys. Alright, this was I-10. This was S with a 2. This was S with a 2. This was S with a 2. And this was a 2. Alright, so we are storing a new 2 in this position. So, in C2, we already have the address 2 in here. I don't have to take it from memory again. I don't have to take it anywhere else, so that's why I'm not passing through the exclusive state right now. But I am going to modify it. So I'm going to modify this. This 2 becomes a new 2. And I don't write through to memory. So this is still the old 2. Any old value that was shared with it, aka this one and this one, are now invalid. Because even though it looks like it's the same value, it's a new write that's happening. And because it's a write miss, we have to mark the ones that were connected to it with the shared bit as invalid. And that's the end of that one. Sorry, that got a little confusing at the end. Is there an order we have to follow when we change the SEM? Like, is it supposed to follow MESI? Actually, you can have an example where it does follow MESI. I always like to think that is literally the order. Here, we go from modified to we flush the value out, exclusive, then we have a shared. If something else was loaded here and invalidated this bit, then yeah, this could go into MESI. It could go into all 4 states. So there's really no, I guess, true order for it, but you can do any of those. So that's totally fine. Okay. Any other questions? Because this is about done. This do not allocate is literally the exact same thing as this do not allocate, so it's totally fine either way. Okay. Okay. Any other questions for this one, or? Yeah, I'm pretty much done here. We could do scan and C-scan. I'm probably gonna stop the recording and do a new one because this one's gonna get too long. Okay, if oh my gosh, since C2 is M, it sends the invalid bit that C3 and C4 snoop to go from S to M. MM is still the old 2 since it's right back. Yes, correct. If it was right through, C2 sends 2, the new 2, to main memory. Exactly, because right through to main memory. So C3 and C4 snoop the new 2 and become invalid. Yeah, exactly. That's exactly what's going on. Okay. All right, cool. I'm going to stop the recording here. I'm going to upload that to YouTube, and then that way, hopefully, by the time the session's over, you guys can go through it again. So let me end that recording.